guys, for this section it will seem as if we're changing the topic a little bit because we were doing antiderivatives in the previous video, and now we're going to be talking about the area under curves and related to the marginal profit and the total profit, marginal revenue and marginal cost, and total revenue and total cost. And the reason will be, while we're doing this, will become evident in the next module when we're going to connect these concepts using the first fundamental theorem of calculus. So for the time being, what we're going to be doing is problems like this. Suppose that you have a marginal profit or revenue or cost. This function can be just about anything, but you have marginal, and it's going to be, in this case, in thousands of dollars per month. And then we have that it's given by this function. Then we would want to determine the total profit, and let's do it for the first and second years. So for the first year, to calculate this, what we're trying to do, since you're doing profit in thousands of dollars per month, if you want to do it for a year, you have to do 12 months. That's because the unit for time, this should be a vertical line, the unit for time is in months. So this is going to give you, whenever you calculate the area under this curve, is going to give you the profit, not marginal, but profit. When you calculate the area of this triangle, you're going to calculate that we're going to be getting the profit of for the company in thousands of dollars. So in this case, the profit for the first, let's say, from for the first year, so I have to do my months from the month 0 to 12, is going to be equal to then the area of this triangle, which is going to be a half of the base times height. So a half of the base is 12 months, and the height is going to be, for this triangle, p prime at 12. So you evaluate this, by the way, this is y equals p prime of t. Oops. So we evaluate it, and you get, in that case, 2.4 thousands of dollars. And so you would have the base of the triangle is going to be 12, and the height is going to be 2.4 thousands of dollars. So you put that here, and you then multiply, and you're going to get, this is going to be 1.2 times 12, which is going to be 14.4 thousands of dollars. So this would be thousands of dollars. So that gives you a profit for your first year. Now, if you wanted the profit for the second year, what you would need to do is calculate the area from month 12 to month 24, which should be right here. That should be a vertical line. And you'd grab the area of this other region, which now it's a trapezoid. And so for the second year, we would have the profit in between 12 and 24. So for the second year, so it would be a half of, now the base of this triangle, since you're going from 12 to 24, is still 12. But now remember that for a trapezoid, you don't do a, you would have to do the average of the heights. So basically that 1/2 is gonna, you have to put the summation of the heights here. So the first height is 2.4, and for the second one you have 24, and if you evaluate it, would be 4.8 when you evaluate it in here. And so this would be 4.8 plus 2.4. and that's going to be equal to 15.6 thousands of dollars. So you're gonna have a few of these examples in your homework. This basically you're calculating the area under the curve using geometry. However, what if I give you a graph like this? So for example, in this case, this is the equation y equals 9 minus x squared. So what if I give you this graph right here? Well, you cannot use geometry, but what you can do is you can approximate it using rectangles. And how do you do that? Well, grab the first rectangle and make it correspond. In this case, I'm going to do it with 3 rectangles. So let's say, oh, I did it wrong. I did it wrong. Try again. There we go. So make it correspond with the x equals 1 and make it correspond to the height at x equals 0. Then the next one, you would grab the height of the function at, well, close to anyways. Let me move it. Well, should match right there. And then make another rectangle. There, and you see how you get the area. You could get the area of the under the curve, but you always get this little extra stuff that in this particular case is extra. You could have some parts missing, but you have that stuff that does not belong to the area under the curve. So you have, this is just a rough approximation, but how would you calculate that? If you would like to calculate that area, what you would do is you first calculate the width of each rectangle, and you call that delta x. And the way you do it, you grab the endpoints of the interval. So if you say this is going to be called, traditionally they call the first endpoint A, and the second one, the right endpoint, they call it B. So you do B minus A and then divide by the number of rectangles you want to make. In this particular case, it's easy because it's 3 minus 0 over 3. And as we drew the rectangles, they have width or base 1. So you have a base 1. Now to calculate the area of each one of them, you just have to find the height. So the first height would be the height here at this point, which corresponds to 0, comma, and the height would be f of 0. Well, I guess I should call this f. And when you evaluate that, would be 9 minus 0, so 9. The next height here would correspond to the point 1, comma, f of 1, which is 9 minus 1 squared, which is going to be 8. So that height is my next height, 8. And this one right here, which I'll make it match with my picture, would be the height corresponding to 2, comma, and when you evaluate your 2 in your function, the height of that rectangle would correspond to 9 minus 4, which is 5. So those heights I'm obtaining just by plugging them into this equation right here. So the height for the third rectangle would be 5. So the area of this rectangle would be base times height, which is going to be 1 times 9. So 9. The base of the area of this one, well, should be all the way down. 1 times 8, base times height. And similarly here, 1 times 5. So the area of this would be 5. So the area, my rough approximation, would be 9 plus 8 plus 5. I'm just adding the areas of each one of these rectangles, and I get that that's going to be 22. Sorry, it scrolled when I didn't need it to. So 22, and let's say units squared, just to denote that it's an area. Okay, I probably, no, never mind. I was going to say I probably should have done the same up here, but no. Here what I did is put my units in thousands of dollars because I do have units. In this second case, we don't have units, so let's just indicate them to say that they correspond to an area. Alright, so for this other problem, if you want to approximate it using 6 rectangles, what you would do is now you have to divide your interval. So let's do that before I start drawing. We divide our interval into 6 rectangles. So your delta x, so the width of the rectangles now would be 3 minus 0, b minus a, over n. I want now n would be 6 rectangles. So the width of my rectangles would be 1/2. So let me go ahead and draw those and I'll be right back. Alright, so I drew them. I took my time and they look a little better than the ones I did live. So now the heights. So the height for this one would correspond to 0, f of 0, which is 9. Remember our function. I'll write it here so we keep it visible. So when you evaluate 0, that's easy to find out. And that is 9. This one will correspond to 0.5. And now the height is going to be f of 0.5, which is 8.75. And you continue like that and you calculate each one of the heights. Let me do that. I'll be right back. Alright, so I get all those heights. I get 9, 8.75, 8, 5.75, 5, and 1.75. Notice that the area of this now wouldn't be 1 because the base is 0.5. So before we had 1 times the height, but because that was the width, but now the base of this rectangle is 0.5 and the height is 9. So that's going to be 4.5. The base of this one is again 0.5. And then the height is 8.75. And that would be 4.35. 37.5, sorry. Got the calculation wrong. And you continue like that and you get all your areas. Now, if you want the area of under the curve, the approximation we're going to get would be the sum of all these areas. So what you can do is you notice that the width I'm using the same for all of them. That's how we wrote each rectangle. So let's factor the width out and just add all the heights. So that makes it a little easier so you don't have to be multiplying a bunch of them. So just add all the heights and then multiply them all by 1/2 once you've done it. And that saves you a lot of time. I want to run out of room, let me put it here. And that gives you 19.125 units squared. Now, this is a little smaller than what we had before, 22. And it's a little closer. If you calculate the exact area, which is something we'll learn in the next module, the exact area for this under the curve is going to be equal to 18, actually 18 units squared. That is the exact value, and we'll learn how to do that, but this is our approximation this time. So you see we're getting closer. As we increase the number of rectangles, we're getting closer, and eventually we're just going to take a limit and let n go out to infinity.